All right, this is going to correspond with day 8, which is called blocking. It is the next type of experimental design, and it is a little more advanced experimental design than what we've been doing, which is called a completely randomized design. So what we're going to start with is on yesterday's classwork, which is called day 7 practice, we started talking about this question and we did the completely randomized design associated with this question. If you recall, it was about the 166 adults who had sinus infections, and we split them in half and put them in 2 groups, one of which received the treatment, which was the antibiotic, and the other one received the placebo. So if you got up to part B yesterday, part B said all the subjects in the experiment had moderate, severe, or very severe symptoms at the beginning of the study. So it talks about if there is an advantage or a drawback of using these kind of people who have moderate, severe, and very severe symptoms versus just using subjects with very severe. So here's the thing. You may have already started this or thought about it yesterday, but basically, if I had separated these 166 subjects who have sinus infections into 2 groups randomly, just by chance, group 1 might have a bunch of people who have very severe symptoms. Okay, and group 2 might have some people who have just moderate symptoms. And you may be thinking, well, what's the problem with comparing the people who have, this is the treatment group, by the way, the amoxicillin, and this was the placebo group, which is the control group. What's the problem with comparing people who have very severe symptoms to people who just have moderate? Because we're going to measure and compare their sinus relief, basically. And you may have thought, well, the severity of the initial sinus infection could actually be considered a lurking or confounding variable that could play a role in the amount of sinus relief. So people who have a very severe sinus infection may respond differently to antibiotic than people who just have a moderate. So we may not necessarily want to compare people who have a very severe sinus infection to people who have a moderate because they might respond differently. So if you think back to our picture, which was the 3 circles, and now this is actually going on to day 8, which is the blocking. You remember the 3 circles represent the X variable is the explanatory variable. The Y variable is the response variable. That should really go on that line. And then the Z variable is that lurking or confounding variable. So if we think that there's some kind of confounding variable that could get in the way of the experiment, then we have a problem because we can't necessarily conclude that the treatment indeed caused the causation of the response. So in the case that we were just talking about, we were talking about using amoxicillin as the treatment, which was the explanatory variable. And the response variable was the presence of sinus infection or sinus relief. But we just said that the possible lurking or confounding variable could be that third variable Z, the severity of the initial sinus infection. So basically we could be confused with if the amoxicillin actually indeed works for all types of sinus infections, or does it only work for ones that are severe, better than those that are moderate, etc. So in this box here on the side, it says our goal is to determine the causation between the treatment, which is the X variable, and the Y, which is the response. But because that lurking variable Z could be present, it might get in the way of us confidently concluding causation, okay? So basically, this is why what we could do instead, and you may have been thinking about this yesterday when you looked at the question, would have been to separate these people into 3 groups. And the 3 groups would have been moderate, severe, and very severe. And then after you separate the 3 groups, then do a separate experiment within each group where you have group 1 and group 2, treatment and placebo, and then you just compare within the moderate group, separately within the severe, and separately within the very severe. Now you may be thinking this sounds familiar. This actually does sound familiar, but in the sampling unit, we called this something different. In the sampling unit, you probably say, oh, this sounds like a stratified random sample. Well, if it were a sample, then indeed we would call this a stratified random sample, and then we would just basically take a simple random sample within each group. Similarly here, we're going to separate them based on the possible lurking variable that we think is going to get in the way, which is the severity of their sinus infection. And then we're going to do a separate experiment within each group. And this has a new name. It is now called blocking, okay? So if it is a sample, let me write it down here. If it is a sample and we're doing regular sampling, the most basic sample is the simple random sample. And if it's an experiment, the basic experiment that we talked about that's akin to the simple random sample is the completely randomized design, using the same principles of simple random sampling to assign treatments. It's just called something different when we call it an experiment. Similarly, when we're doing a sample, when we separate people into groups, first based on something they have in common, it is called a stratified random sample if it's a sample. But as soon as it becomes an experiment where we're assigning treatments, now it's going to be called a randomized block design. Okay. So it really is the same thing. We're just now going to give treatments to the subjects. And so now it becomes an experiment and we use the word blocking instead of stratifying. Okay. So keeping in mind, these are quite similar concepts. Now the goal is slightly different though. The goal for the stratified random sample is to guarantee representation of every group and basically then reflect the differing opinions, if there are opinions, if it's like a survey or something, between the groups and grouping the people who are most similar together as well. But with the experiment, the goal is to reduce the effect of the confounding variable that could get in the way. So the blocks are like the strata. It is the grouping of individuals, subjects, or units, depending on if they're human or not, based on what they have in common with respect to that lurking variable. Which I'll call a confounding variable here. Okay, so in the sake of the question example that I just said, the blocks would have been, the three groups would have been the moderate, the severe, and the very severe. So there would have been three groups, aka three blocks. And then what I would have done within each block or within each group is the same design that I have structured here, but basically within each group. So what I would do is group 1 would be block 1 would be moderate people. Group 2 would be severe. And group 3 would be very severe. Okay. So maybe I had 100 people who were moderate. Maybe I had 30 people who were severe, and maybe I had 36 people who were very severe. Okay, I just made them even for the sake of ease. So now basically what I'm going to do is I'm going to separately do a completely randomized experiment within each block. Okay, so these are the blocks. I'm going to write block by severity of sinus headache. And then I'm going to, within each block, now I'm going to do the randomization process. So I'm going to order the people, number them, use a table of random digits to randomly select half of them. So it'll be 50 unique 3-digit numbers to go to group 1, treatment 1, which is the treatment group, amoxicillin. Okay, and that's 50. And then I would send the remaining people who were not chosen to group 2, 50 people, treatment 2, and they would be the control group, so they would receive the placebo. Okay, and then at the end, I would measure and compare the degree of the sinus relief just within the moderate people. And basically, I'd be able to more confidently conclude causation that indeed the amoxicillin is causing better sinus relief among the those that have a moderate severity of sinus. And now then I would basically repeat the process for the other two. So I would do it again for severe, group 1, group 2, treatment 1, treatment 2. Then at the end I would measure and compare the results within just the severe. And then same thing, so very severe, group 1, group 2, treatment 1, treatment 2. And then at the end I would measure and compare the result within the very severe. So maybe across the board, I noticed that the amoxicillin is indeed doing a better job than the placebo. So not only do I see amoxicillin did better with moderate, amoxicillin did better with severe, amoxicillin did better with very severe. So then across the board, I can make a generalized statement and say, oh, I'm confident actually that amoxicillin is the best for sinus relief. So I'd measure and compare across the 3 blocks. Okay. Maybe I noticed that amoxicillin does significantly better with those that have the very severe, but then within the other groups, it doesn't. So maybe then I realize, all right, amoxicillin only really works well if you have a very severe sinus headache. Otherwise, meh, not so much. Okay, so basically the reason why this is good is now I can remove the confounding variable of severity of headache and not necessarily compare people directly to each other who are too different initially, all right? So that is what I just described as the randomized block design. I'm going to write down the steps that I just described. So the first step I did was I separated the subjects or the units into blocks based on something they have in common, which I wrote above is the possible confounding variable. After I do that, step 2, now I'm going to conduct a completely randomized design experiment within each block. Which means I'm going to randomize treatments within each block. And then what I'm going to do is I'm going to compare within the blocks and compare across the board. To conclude causation of treatment, basically. So I know that was a lot, but I'm hoping that it makes sense to you because it kind of is related to stratifying and that you're separating the people first based on what they have in common. But the key here is with respect to the possible confounding variable, okay? So some of the most common examples of blocking that they like to do, common ones, are gender, because they think sometimes that gender really does play a role in certain things. So like sometimes there's like a greater level of heart disease among women than men. So gender is a common block. Age group is a common block because, you know, with age, a lot of things can change. Ethnicity, race, that can play a role in a lot of different health problems depending on what race you are. You may be predisposed to certain conditions more than others. Things like that. When we get into animals, different breeds of animals can actually react differently to things as well, which we're going to see, okay? So now if you advance this a little bit past that, we did this and go to this. This is kind of a picture of what I just explained is the blocking situation. So we might use this for a further question. I'm just going to leave this for a second. We said an advantage of blocking is to reduce the effect of possible confounding variable. Okay, so don't say to remove bias. That's something totally different, and that has to do with sampling a lot of times, but this is not the case here. Okay, so let's look at this example. There have been many studies recently concerning coffee drinking and cholesterol levels. So I'm already thinking that coffee drinking is the explanatory, cholesterol is the response. While it is known that several coffee bean companies can elevate blood cholesterol level, it is thought that a new type of paper coffee filter may reduce the presence of these components. The effect of a new filter will be studied over a 10-week period using 300 non-smokers. So keep in mind all these subjects are non-smokers who each drink 4 cups of caffeinated coffee per day. So it sounds like they're always drinking coffee, all these people. Each of these 300 participants will be assigned to one of 2 groups, the experimental group who drink the coffee that have been made in the new filter, and the other group is the control group, and those are going to be given the standard filter. So there's 2 treatments, new filter for coffee and standard filter. Each participant's cholesterol level will be measured at the beginning and at the end. So it looks like they're looking for the change. So if you look at part A, it says describe the appropriate method for assigning the groups. So to me, this is already a completely randomized design, which we did yesterday, okay? But if you look down below to letter D, D says, why would the researchers choose to use only non-smokers in the study? And this is really what I wanted to get at when I'm talking about blocking. We want to try to keep a level of control as much as possible by controlling for all the other variables at stake. So we only want to use non-smokers because if we're measuring cholesterol, the presence of being a smoker can play a huge difference in your cholesterol. So we want to remove the lurking variable of being a smoker. So the answer to this question down below would be we want to keep it as consistent as possible. Consistent, spelling wrong. With respect to cholesterol levels, because smoking status can be a possible confounding variable when it comes to cholesterol increase specifically. Okay, so let's say that instead of them saying that there were 300 non-smokers in the study, let's say that they had just all types of people in the study, okay? Maybe they had 200 non-smokers and they had 100 smokers. Then what we could have done would have been to block on the smoking status. So what we would have done, if you look back at my weird diagram that looks kind of scary, is you would take your 300 overall participants, which are subjects because they're humans, and then basically we block on smoking status. So we would have the non-smokers over here, 200, and we have the smokers over here, 100. So I'm blocking on the possible confounding variable of smoking status. Notice I have not done any randomization yet at all. I've just deliberately separated them based on what they have in common with respect to the lurking variable. And then I would now do the steps that I need to do within each group. So I would order the participants, number them, use a table of random digits or the random number generator, and randomly assign the corresponding groups. So now the randomization process happens here. I go to group 1, treatment 1, new coffee filter. Group 2, treatment 2, standard coffee filter. So I would have 100 and 100 just of non-smokers, and now I'm going to measure and compare the cholesterol level within the non-smokers. And maybe I see, oh, it looks like the new filter really helped and reduced the cholesterol among the non-smokers. Okay, check, check. Now I'm going to do the same thing, a separate experiment within the smokers. I'm going to randomly assign them to treatment. So I'm going to order them alphabetically by last name, number them, use a table of random digits or a random number generator to randomly select half of them to go to group 1, treatment 1, new filter. Send the remaining 50 to group 2, treatment 2, standard filter. Now I'm going to go just to the smokers and I'm going to measure and compare their cholesterol change. Now maybe I just look at the smokers and I say, oh man, across the board, the smokers also had a better cholesterol outcome with the new filter. So now, lastly, I look across the board at both smokers and non-smokers, and I measure and compare the cholesterol changes among both. And maybe I see overall, it looks like indeed, whether you're a smoker or not, your cholesterol was reduced better with this new filter for the coffee, so I'm going to now feel more confident in concluding causation with respect to that filter.